Welcome back to chapter 20. In this chapter, we're not going to be learning about any type of new test or interval. We're just going to be looking a little bit more at tests and intervals in general. We're going to look more at the hypotheses, what the p-value means. We're going to look at errors, things like that. So first of all, we have the null hypothesis. Now the null hypothesis does have some special requirements that have to happen. First of all, it has to be a statement about the parameter. So your null hypothesis is going to look something like h naught such that p equals something. Or later on, we're going to get means. It'll be mu equals something, not x bar, not p hat. Those are statistics based on the sample we have. We're not trying to say something about our sample. We're trying to use the sample to test something about the population. We use the value to compute the probability that the observed sample statistic is, or something even further from the null value might occur. That is the p-value that we find. That is the probability of getting the results we got, or something more extreme, if the null hypothesis is true. That's the p-value. So how do we choose it? It comes from the problem. It will be like in what we're doing, it'll be stated in the problem. Or it should be obvious from the problem a lot of times. I've used the example of testing a dice to see if it's fair. The probability of rolling any given number would be 1/6 if it's a fair dice. Sometimes, as I've mentioned in the past, the null hypothesis can come from previous knowledge or from a larger population if we're trying to say that a smaller subpopulation or even a different population is somehow different. But generally speaking, with what we're doing, since you wouldn't necessarily have any intuitive knowledge of the random situations that problems would present you with, it would be given in the context of the problem. So good way to think about it is the why of the situation. Why are you doing this? You are trying to show something. You're trying to make a claim against the population. The thing that you are trying to prove is true is not the null hypothesis, because you cannot say the null hypothesis is true. There's either evidence to reject or there's not evidence to reject. And you can't just choose anything. It has to relate to the question at hand. It's context dependent. So again, you cannot prove the null hypothesis. So the one you want to show is the alternative hypothesis, that it's greater than or less than something. Therefore, if you reject the null hypothesis, what you end up with is true. So the p-value, it is the probability of getting what you got if or given that the null hypothesis is true. It's not the probability that the null hypothesis is true. It's very similar to that, but stating it that way would be, it's very tempting, but it's not quite correct. It's more than just incorrect grammar, but not a whole lot more than that. It's not even the probability that the null hypothesis is true given the data. It's the probability of getting the data you got if the null hypothesis is true. We assume the null hypothesis is true, and then we look at the data. Was our data surprising, or was our data not surprising? That's what we're looking at. And so do be careful to interpret that p-value correctly. On the AP test, that can be the difference between an essentially correct and a partially correct, by interpreting the p-value incorrectly. So with a high p-value. So when we have a small p-value, we could believe the null hypothesis, and it's like, yeah, we saw that rare event. Like by chance, we happen to get this data that's completely against what we expect. But that's not really why we do the test at all. We get something against what we would expect from the null hypothesis. Hey, that gives us good evidence to reject the null hypothesis, to say that it's not true, which is what we're really trying to do most of the, like generally speaking, we're trying to reject the null hypothesis. However, big p-values doesn't mean what we observed isn't surprising. It's just that it's kind of what we thought that we'd see, or it's not far enough away from what we thought that we would see. And so we don't have any reason to reject that null hypothesis. Again, a big p-value doesn't prove the null hypothesis is true, but it doesn't offer evidence that it is not true. It's kind of like we go back to the court case. Someone's on trial for committing some sort of a crime. Well, his car didn't go to the crime scene. All right, so that doesn't, I mean, if his car was at the crime scene, that would be good evidence that he was guilty. But if his car wasn't at the crime scene, well, that's not necessarily evidence that he's not guilty. It's just not evidence that he is guilty. So that's kind of what that is. So when we see large p-values, we just don't reject the null hypothesis. Sometimes we need to make an actual decision, like we need a baseline about whether to reject it or not. And so when the p-value is small, it tells us our data is rare given the null hypothesis, but how rare is rare? For that, we use an alpha level, or a level of significance. So making a firm decision is one of those things that is kind of wishy-washy. Like there's no line that's cut or dry where it's significant or not significant. We're going to see that a lot of times we use 0.05. Well, 0.0499 and 0.0501 has no difference between those values for any purpose. It's just one is less than 0.05, one is bigger than 0.05. So if we have to make a decision, we have that baseline. That's what we have it for. We set it before we gather our data. It's kind of the same thing as grades. A 90% is an A. I'm going to ignore minuses and stuff like that. 90% is an A. There's really no difference between someone that has an 89.99% and a 90.01%, except one person reached that benchmark and one person didn't. But if we move it, it's like, all right, well, that 89.99%, that's close enough. What about that person that got an 88%? Oh, and then what about the 87%? And what about the 85%? And so having that cutoff just gives you that marker, that line to go by. And that was a lot more prevalent in the past before we had technology, because we couldn't necessarily find very accurate p-values. And so we took the p-value that we'd get, we found a z-score, and then we compared that. It was a critical value. Is a z-score that would correspond to the p-value, the alpha level that was significant. Now that we have the ability to find fairly accurate p-values, we report that, and we generally let people make their own decisions on things, giving them, like, there's strong evidence to reject, there's some evidence to reject, there's little evidence to reject, but the p-value itself gives more information than just a reject or not reject. So, but how rare is rare? So we arbitrarily set that threshold for p-value. And if our p-value is below that point, we reject the null hypothesis, and we call that statistically significant. We'll talk more about statistical significance in just a little while. The threshold is called alpha level. It's denoted by alpha. Generally speaking, in statistics, this is the only place alpha is used. It's the alpha level. Later on, we're going to see a beta. We use beta a couple different places, but alpha is pretty much here, just like pi is used in one place, I is used in one place, alpha is used in one place. So the common alpha levels are 0.1, 0.05, and 0.01. And you have the option to consider your alpha level carefully and choose an appropriate one for the situation. Generally speaking, that 0.05 is a kind of the standard alpha level. Depending on the situation, depending on how much evidence we need to change people's thought. Like if this is a deeply held belief, we might need a 0.01 alpha level. If it's something where we're just trying to make a decision, a 0.1 would be fine. If it's like, well, do we want to go with option A or option B? Hey, option B has higher results at a 0.1 level. Cool, let's do that one. And so it is definitely related to the situation, the context. But 0.05 is kind of the standard. On the AP test and in problems that we do, a lot of times you will be given an alpha level. Use what you're given. If you are not given an alpha level, you can pick one. It doesn't really matter what you pick. Generally speaking, if you're not given an alpha level, like on the AP test, you're not going to get something close to these numbers. You're going to get like 0.003 or 0.24, something that's way higher or way lower than any reasonable alpha level. So regardless of which one you pick, it works. Now let's say that you actually got one that's in the middle, or you made a mistake and you ended up with, say, 0.3 or 0.03. If your alpha level is 0.05 and you reject the null hypothesis because 0.03 is less than 0.05 and you make that connection there, you will get the points for that. If you chose an alpha level of 0.01 and you do not reject the null hypothesis because 0.03 is greater than 0.01 and you make that connection, then you would get the points for that. So it's not like a reject or not reject. It is tied to what you picked for your alpha level. So you can pick different alpha levels, get different results, but still end up with correct answers. When we reject the null hypothesis, we say the test is significant at that level. Let's say that we do not have an alpha level, so we pick 0.05 and we get test results that are, say, 0.003. It's like, hey, that is significant at alpha equals 0.05. In fact, that is significant at alpha equals 0.01. Like, we can even, like, point out there that's like, hey, this is even, like, it's significant at the smaller alpha level. Just shows that it's more evidence against that null hypothesis. So what can we say if the p-value does not fall below alpha? Well, you haven't rejected the null hypothesis. The data have failed to provide sufficient evidence to reject the null hypothesis. Do not accept the null hypothesis. We've said that numerous times in the past chapter, saying it more, and I'll be saying it more later on. You never accept the null hypothesis. You either reject or you fail to reject. Because remember, just like in that jury trial, you don't find someone innocent. They're either guilty or they're not guilty. And what not guilty means, it doesn't mean that they're innocent. It means that enough evidence has not been provided to show beyond a reasonable shadow of a doubt that they are guilty. Like, I mean, that's just the way it is. You don't say they're innocent. So, as I mentioned before, the p-value gives readers far more information than just stating that you reject or fail to reject the null hypothesis. So always provide that p-value. And you, by doing that, you allow that person to make their own decisions about the test. Because what you consider significant might not be significant to other people. And as I said, there's more than one alpha level that can be used, but each test will give only one p-value. It's just, does it fall above or below the alpha level that was used for that test? And then what do we mean when we say that a test is statistically significant? That the p-value was below the alpha level. That's what it means. It means that the data was far enough away from the mean, or away from the null hypothesis, that there's a small amount of chance that it was due to chance alone, and so it was probably due to something else. So that's statistically significant. However, statistical significance and practical significance are not the same thing. I mean, it could, if we have a super high sample size, that puts the variability down to almost nothing. And hey, we've increased, by using this thing, we've increased SAT scores by 1 point. Well, that means nothing. Like 1 point, it's like, oh, hey, we increased them from a combined 1350 to a 1351. That's meaningless. Like there's no difference there between those two values, and that's called the effect size. So I used a mean, so let's do a probability. So we have our null hypothesis. We think that the probability is 0.2, but with our sample hypothesis, we got 0.21, so it was 21% instead of 20%. It's like, well, yeah, we had a big sample and it came back that way and it gave us significance because our standard error was so low, but 1% doesn't really make much of a difference to anything. So that's a really small effect size. And the practical importance is minimal, even though it could have possibly been statistically significant. So for larger samples, even small, unimportant deviations from the null hypothesis can be statistically significant. That's what I just had mentioned. However, if the sample is not large, even a large significant difference may not be statistically significant. Instead of that 20% null hypothesis, we got 35% for our sample. However, since our sample size wasn't very big, our standard error was so big, it didn't count. So it wasn't far enough away, even though that's a pretty big deal. So it's a good practice to report the magnitude of the difference between the observed statistic value and the null hypothesis value with units, that would be in context, along with the p-values. So with a p-value of 0.002, there's strong evidence to reject the null hypothesis, saying that it was bigger than 0.2, and we got 0.35. Like our sample gave us a sample proportion of 0.35. So far we've looked at confidence intervals and hypothesis tests. And both of them just one sample proportion ones for now. So they're basically the same thing. They're built from the same calculations. They're both finding those z-values. They both take that normal curve, and we're going standard deviations away from the mean. they have the same assumptions and conditions. The difference, again, is that a interval, we're trying to estimate that population proportion. With a test, we are testing a claim against that population proportion. But you can approximate a test by using a confidence interval, because if we have a confidence interval, I'd say a 95% confidence interval, 95% of the samples we take are going to include the mean, which means they would be in this area where we would reject out here. So if in your confidence interval you include the null hypothesis value, that would be failure to reject the null hypothesis, because that's a possible value that you would estimate. If in your confidence interval that does not include the null hypothesis, that means that there's good evidence to reject the null hypothesis. And so, confidence intervals with two-sided tests are super easy, because the confidence percent is basically the same as the alpha level. It's just the other part, so it's 100 minus that. So if we wanted a two-sided test, which, remember, a two-sided test we would reject if it went either way, and the alternative hypothesis would be p does not equal whatever that value is, so it goes either way. We get, it's the same as that confidence interval, only the other piece, because that is split on each side. With one-sided ones, it's a little bit more complicated. So we have to have an alpha level we subtract, and then we have to do half of it. So if we wanted a alpha level of 0.05, we would need like a 90% confidence interval, right? So it's easier. So we have, you can, alpha equals 1/2 times 100 minus c percent. So 2 times alpha would equal 100 minus c. So if our significance level of 5%, that puts us up to 10%, which means we need a 90% confidence interval. Which you can still do. It's just, you have to be just a little bit more careful. So, errors. I love it. Nobody's perfect. So, we could still make the wrong decision here. There are two basic errors that we can make when we're doing a significance test. And this isn't about like wrong conditions or assumptions or miscalculations or things like that. We're pretending that we did everything right. However, our sample, like, we have that sample variability. When we have that alpha level of 0.05%, that means that 95% of the samples we would take would fall within that, but there are 5% that would fall outside of that range and give us significant results, even if that null hypothesis is true. And that is a type 1 error, and these types are like defined names. Like, the null hypothesis is true, but we mistakenly reject it. That's a type 1 error. That would be a false positive. We're rejecting it, but we shouldn't. And that is also sometimes called a false alarm. It's like, hey, we tested positive even though it's not positive. And so you get all worked up because you're tested positive for something when in fact it is negative. That's a false alarm. So there's the rejecting it when you shouldn't, and then there's also not rejecting it when you should, and that's a type 2 error. So type 1 error, we reject it when we shouldn't. Type 2 error is a false negative. We don't reject it when we really should. Like it was significant, however the data we got happened to not be. So here's a good description. I know the book does a good job. It says type 1 error, that's like Chicken Little. It's like, hey, the sky is falling, the sky is falling. Well, no, it's actually not. The type 2 is, or not type 2, this one is Sherlock Holmes. Do a bunch of investigating, you find it, it's interesting, it's correct. This one down here, which is also not an error, is, they call it a sad sack. It's the, no, that's the Bilbo Baggins. He's not going to find any adventure because he never goes on adventures. And so it's there. There's no adventure, there's nothing to see, but that's fine. And then the type 2 error is the sad sack, where there's something interesting, but the data you got just didn't give you the interesting stuff. And so, which is more serious? Depends on what's happening. If we're looking at a court of law, a type 1 error would be not guilty for someone who is guilty. So someone that's guilty walks free. A type 2 error would be sentencing an innocent person and putting them in jail. Which of those is more important? Well, or which is more serious, more problematic? Really kind of depends on your point of view and which person you are there. In medical stuff, a type 1 error is if you test positive for a certain disease, even though you don't have it. A type 2 error is you test negative for the disease, but you do have it. Well, if you test positive, then they might start treating you. They'll probably run extra tests, find out, oh, wait, no, I guess you don't have it. If you test negative for the disease, then they're like, okay, you're healthy, you can go. But it turns out you have the disease, and that's not going to be good for you. So, in that case, the type 2 would be more serious. So how often will that type 1 error occur? So it's rejecting the null hypothesis when the null hypothesis is true. Well, we reject it at that alpha level. Let's just say 0.05. That means that if we get that probability less than 0.05, or that p-value is a probability of getting the results that we got if the null hypothesis is true. So the probability of getting those results that would reject it if the null hypothesis is true is just the alpha level, whatever that is, 0.1, 0.05, 0.01, and 0.05 would be 1 out of 20, by the way. So it's not way out there, but 1 out of 20 is fairly it's fairly rare. So the probability of a type 1 error is just the alpha level. When H0 is false and we reject it, well, that's good. That's the right thing. And that's actually called the power. And the power is the probability of rejecting the null hypothesis is actually false, and it is 1 minus the probability of a type 2 error that we're going to see here in a second. In the past, you guys have had to find that probability of power and the probability of a type 2 error, which is not the easiest thing to do in the world. You don't actually have to do that anymore. So you guys are a little bit lucky on that. So when H naught is false and we fail to reject it, that's a type 2 error. So we're going to say that beta is a probability of making that mistake. It's harder to assess beta because depending on what the parameter is, and depending on what our alternative is, we get a whole bunch of different betas. Like how far away, what is that error value that we get? Each of them is going to have a different beta. The further away from beta from the null hypothesis we get, the less the beta is. And so we'll have this probability or this power if the parameter equals this other thing, it has this power. So it gets kind of weird. So one way to focus our attention on a particular beta is to think about the effect size. So what other value do we want to use? How big of a difference would actually make a difference? So if we're at 20% and we think, 5% difference, so 25%, that would be a significant enough difference. We could use that to find the beta and to find the power of the test for that value. We can reduce the beta for all of our alternative parameter values by increasing the alpha level. However, that would increase the alpha level, but it would decrease the chance of a type 2 error. So it increases the chance of a type 1 error, decreases the chance of a type 2 error. And so that happens. When one goes up, the other goes down. It's a natural thing. You cannot get rid of all the error. It can't happen. It's one of those things about statistics. Like there's going to be that variability. Did we get a sample that is a good descriptor of what's actually happening, or did we happen to get one that wasn't? Even though we weren't biased, there was nothing going on. We just happened to choose a sample that gave us not so great results, or results that didn't adequately reflect the population we were taking them from. So the power of a test is the probability that it correctly rejects the false null hypothesis. When the power is high, we can say that we've looked pretty well at it. So the power of the test is 1 minus beta. Since beta is the probability the test fails to reject the null hypothesis, not failing to reject the null hypothesis is the opposite of that, so it's 1 minus that. When a study fails to reject the null hypothesis, the test's power comes into question, especially if we think that it should. When we calculate power, we imagine the null hypothesis is false, and I'll give you a little diagram of what we're doing here in just a couple slides. The value of the power depends on how far the truth lies from the null hypothesis value. The distance between the null hypothesis value P naught and the truth P is called the effect size. We've seen the effect size. And then the power depends on that effect size. It depends on that distance away from the mean. The sample size will change the power. It changes the probability of a type 2 error because it shrinks the standard error. But increasing the sample size can also be really expensive. And it also makes sense if the more willing we are to make a type 1 error, the less likely we will make a type 2 error. So we could always increase. So instead of an alpha of 0.05, we can have an alpha of 0.1. more chance of making a type 1 error and getting that false positive, but there's less of a chance of making that type 2 error and getting a false negative. The amount of unexplained variability, and so that would be trying to control that standard deviation, that standard error, or to control the amount that it changes. Sometimes we can control it a little bit, sometimes we can't. So getting that small variability in p hat can be big. So stratifying can potentially increase the power of significance because it reduces the sample variability. Anything that reduces the variability, changing, not changing, but well, it does change, but refining the population that we're looking at can sometimes reduce that variability. And so there are things that we can do to reduce that, and that can help to make a test more powerful. And so, in summary, power is greater when the following are true. The significance level alpha is greater, but significance level alpha is greater. That leads to a greater chance of type 1 error. The effect size is greater, but that's based on the population and the null hypothesis, which neither of those we can really control. The sample size is greater, but again, costs more money and resources. Variability from extraneous sources is reduced. That can be done by changing the way the data are collected, different ways of doing that. And so what is this power, this type 2 error? What's going on here? So we have our population, but this is our null hypothesis. So this is P naught. And we go out 2 standard deviations. So we're going to reject if it's there. I'm going to use a one-sided test here. We're going to reject if it's over there. Well, that's what we think is going on. However, what's actually going on is our P naught is actually over here. Or our P naught, our actual P value, is actually over here. And so what we would do is we would find this value. So the type 2 error is failing to reject when you should reject. So when you fail to reject, that means you get something in this area. So we find what is the probability of getting something in this area if this is our null hypothesis. Remember, when we find the type 2 error, we assume the null hypothesis is false, which means that this alternative hypothesis is true. This distance in between them is that effect size, or the error size. So the P naught could be 20%, the P could be 25%, so that would be 5% difference there. Technically speaking, we would also reject if we were over here, but the probability on that for P naught is so small that it doesn't actually make a difference. So we look at the overlap. Like, the bigger the overlap, the bigger the type 2 error. So the further away these two P naught and P's get, the smaller the overlap is. The less variability we have, the tighter the normal curves get, like the steeper they get, the less overlap we have. So anything that reduces the overlap between those two will reduce the probability of a type 2 error, which increases the power. If you really want to know how to find this, I can tell you how to find this. I can show you that, but we don't need to go into that right now. What can go wrong? Don't interpret p-value as the probability that h0 is true. Remember, the p-value is the probability that we got the data that we got given that the null hypothesis is true. We're assuming the null hypothesis is true. This is the probability that we got what we got. So it's about the data, not the hypothesis. It's the probability of observing data. Yep. Don't believe too strongly in arbitrary alpha levels. So again, report the p-value. Let the people make their own decisions. Don't confuse the practical and statistical significance. Because just because it's statistically significant doesn't mean that it's a big enough difference to matter. And just because it's insignificant statistically, I mean, there could be a huge difference there. If your sample size is small, that could be a reason why you didn't get the significance, even if there should be. You can still make a wrong decision. That's why we have these errors. We like to get those closer to zero, but they're always going to be there. And as one goes down, the other one goes up. Don't test multiple hypotheses. And that also goes for don't perform tests more than once. There's a great example in the book on this. It's actually in the form of a comic. And it was on jelly beans cause acne, and they do a test. And it's like, no, they don't. Then they're like, oh, but we heard it was different colors. So they test every single color. And well, one of the colors came back as, hey, it was significant. Well, at a significance level of 0.05, if the numbers are around in there, 1 out of every 20 times we would expect to get one that's significant, even if it's not. We'd expect to get a type 1 error at some point in time. And so continuing to run the tests until you get the result that you're looking for, I mean, I mean, yes, likely. Eventually you will get the result you're looking for, but that is a fluke. It doesn't mean that that's actually a good result. So don't test multiple hypotheses or run tests over and over and over again. So what have we learned? There's a lot more to hypothesis testing than simple yes or no. The small p-value indicates evidence against the null hypothesis. Not that it's true. A lot of people switch that up. They're like, oh, the p-value is super small, so the null hypothesis is true. Nope, other way around. Alpha level establishes the level of proof, which we could take that to the z-value, and then we would just find the z-value instead of the p-value, and we'd compare that. We generally don't usually do that anymore, but it's the same basic idea. Hypothesis test gives answer to decision about parameter. Confidence test tells us the plausible values of the parameter. So the confidence interval estimates the parameter. The hypothesis test tests against a parameter. Then we've learned a couple types of errors. Type 1 error, reject a null hypothesis when it's true. Type 2 error, we fail to reject the null hypothesis when we should reject it. The power is the probability that we reject the hypothesis when it's false, like when we're supposed to. So it's 1 minus the probability of that type 2 error. And then the larger sample size increases the power and reduces the chance of that type 2 error. The AP tips: be prepared to describe what a type 2 or type 1 error would look like in the context of a given set of hypotheses and the consequences of that error. Finding the type 1 error is a super simple, it's usually a part of a question, like it's a part of part A. And you don't have to find the probability of the type 2 error anymore. So that's nice, but you do need to describe them in context, what they mean. And then again, you can choose any alpha you like when you do a problem. But if it tells you to use a specific one, use a specific one. And regardless of which one you choose, if it doesn't tell you, you just have to use it appropriately, and always make sure to connect it to the p-value and the decision that you made. So this was chapter 20. Again, there were no new tests or anything like that, just some more details on this. We'll get to new tests again in the next chapter. But until then, I'll see you in class. Keep working problems, keep asking questions, and as always, happy mathing.